much for being here and giving us her talk. So unfortunately, Dawn will not be able to speak in the workshop, but we have Ruoxi.
Thank you for the introduction. So I'm Ruoxi Jia, and it's a great pleasure to be able to present here. So today I'll be sharing two perspectives on how to mitigate privacy issues in cyber-physical systems. Firstly, what are cyber-physical systems? They are a combination of computational unit and the physical environment. So we have some computational unit interact with a physical environment. It gets information from the sensors, and it also has these controllers that can control the environment. So indeed, actually, a lot of most exciting innovations today are cyber-physical systems. Examples include smart buildings, smart grid, and smart transportation systems. Although those systems are very different from one another, but one thing that they have in common is that they are all data-rich, generate a gigantic amount of data. So actually, then there is a problem about privacy. So for the first building that I showed here, it is considered the greenest building in the world. It is office space of the consulting firm Deloitte. And this building is packed with 28,000 of sensors, and it generates the data, all the way from temperature, energy usage, to when the coffee machine needs to be filled up. So as you can see, this is a lot of data. Although some of the data may seem harmless, like temperature and energy usage, but what I want to show you next is that actually we can easily infer some private sensitive information from those seemingly harmless data. So here is example, this is a snapshot of the smart meter data taken from a household. And you can see that it is very clear when this family is taking vacation and when this family is at home. So actually, your smart meter can become the best friend of burglars. So they can look at the data and decide the level of occupancy at home, and then in order to determine when to send teams to break in. So how can we really go about these issues? So I want to share some challenges for dealing with these privacy issues in cyber-physical systems. So firstly, in those systems, the demand for accuracy is really, or for data utility is very acute, because these systems are oftentimes safety critical. For example, in smart buildings, we use sensor data to determine when to turn on the air conditioning, and we cannot afford to making the office space too hot or too cold. So we really want to push this curve of privacy and utility trade-off. And also, so we have seen that the system is often closed loop, and the data is used in a control application. So how can we really model data utility in this context? And as we have seen before, some data are actually seemingly harmless, but if you assume the attacker has some ability to do some inference, then there will be a lot of privacy-sensitive information come out. So how can we really model privacy loss in this case? So in this talk, I will be sharing two perspectives to solve this problem and really to optimize the privacy utility trade-off. So the first idea that I want to lead through is that we want to follow this principle that the data is actually owned by people, and individuals should be able to control the dissemination of the data. And any entities that try to that can benefit from the data should properly compensate the data owners. So the first idea is that how can we really pay people for using their data? So when it comes to the payment, a natural question is that how can we guarantee fairness? This is a very important question. And secondly, I will introduce some approaches to model privacy loss, model data utility, and therefore formulate an explicit optimization problem to solve for the optimal privacy mechanism. So let me start with the first work, the data evaluation work. So I want to give a special call out for all my collaborators, without whom this work wouldn't be possible. This is really a collaboration between these amazing people from Berkeley, ETH, and also UIUC. So I want to study the data evaluation problem in the context of machine learning. So imagine we have some individuals who contribute some of their private data, which are images. So in machine learning, we want to train a machine learning model based on those data. And the hope is that when the model sees some, some unseen data, it can predict its label very well. So in machine learning, it is natural that we know that the training data is not used in isolation. They have correlation and they have interplay with each other. So the natural idea is that we can actually model machine learning process as a coalitional game, where each data contributor or each people who contribute their private data is a player in the game. So if we have n data contributors, then there will be n players in the game. And another important component to formulate a coalitional game is so-called utility function. So what is utility function? It really defines a score that measures how useful a subset of a collation is. So in machine learning context, it can be the testing accuracy or prediction confidence. For, let's say, for the regression test, it can be R-squared score. So it is really flexible and context dependent. So we can actually use this framework to consider a lot of machine learning tasks. So then the
technical question, are you going to use that in the payoffs to a cooperative game?
Yes. Yeah. So then the million-dollar question is that how can we actually attribute the benefit created from the aggregation of the data to each data contributor in a way that is fair, reasonable. So here we adopt a you have predicted. So here we adopt a concept from cooperative game theory. It's called Shapley value. So it defines a way of distributing the profit of a collation of all players. And it was first proposed by this Nobel Prize winning economist Lloyd Shapley in 1950s. And why it is interesting is that it is mathematically proved to be the only distribution that satisfies a collection of desirable properties. And it turns out all those properties has very close connection with some real-world interpretations, so which I will talk more later. So let us first look at what is the definition of Shapley value. It is actually very intuitive and very simple. So U here is a utility function, and S defines a subset of players. So capital I here is just a notation for all the players in the game. So if there are n players, it will be 1 to n. And as I said, S is a subset. Essentially, the thing in the bracket, it measures what is the marginal contribution of player I when it is added to some subset in the collation, right? And the Shapley value, if you look at its form, it defines the average marginal contribution of a player. So it essentially measures how important this player to this collation of other players. So in terms of its properties, the first property it satisfies is that its group rationality. It says that the Shapley value of each player will add up to the profit that is generated by the collation of all players. So why it is called group rationality is because any rational group of players would expect to share the full yield of the game instead of part of them. And the second property is very interesting. It is kind of connect to the fairness of the payment. So it says that if two players I and G, they have the same utility when being added to some subset in the collation, then they will have the same Shapley value. And the second is saying that if some player I have the actually have the same introduce zero utility difference when being added to a subset, then its Shapley value is 0. So this is really saying that if we consider a group of data contributors, what matters to their data's value is not their names. The value only depends on like how useful their data are, or how much is their contribution to other set of players. And the third property is called additivity. It means that if we have two utility functions and we want to compute the Shapley value under two utility functions, then it will be equal to the Shapley value under each utility functions. Why it is interesting is because oftentimes, our data is used for multiple applications. It will be used for multiple times. And for each application, we can characterize it by a utility function. And this is saying that if our data is used for multiple times, then the values that we deserved from those multiple applications is equal to the values that we receive from each application. So actually, we are not the first one who think about Shapley value and use Shapley value for values of private information. Actually, back to 2001, there is a seminal work by Kleinberg who tried to use this Shapley value to value the private information. And then later on, there are some follow-up works. But the common challenge that are faced by those works is that Shapley value is extremely hard to compute. And also, for that reason, all of those works are focused on some stylized examples where Shapley value is can be analytically derived. So to see why it is very difficult to compute, we can see that we can go back to the definition of Shapley value. You can see that in order to compute it, we need to evaluate this marginal utility over all subsets of the players in the collation, and there are essentially exponential number of them. So computing Shapley value will require exponential time. And if it considers the Shapley value in the machine learning context, it will be even harder because even evaluating this utility function is very hard because if we consider it to be the testing accuracy, it requires us to train a new model on the new subset of data and then calculate the testing accuracy. So in summary, it will be very hard to compute the Shapley value. But on the other hand, there are some opportunities to calculate the data value if we put it in the machine learning context. Let's say if we consider some specific utility function associated with machine learning models, let's consider a very simple one, the k-nearest neighbor classifier. So let's define the utility function to be the testing accuracy of a nearest neighbor classifier. Namely, we want the utility to be 1 if the label of a test point agrees with the label of its nearest neighbor and 0 otherwise. So let's say this is the training point and the test point is a black dot, and you can see the red dot will be its nearest neighbor. So if we consider a subset S, and let's say we want to compute the Shapley value of this player I, we can see that if we want to evaluate the marginal utility of the player I, it will be 0 because the utility is completely determined by the nearest neighbor, and adding I to this subset S wouldn't change its utility. So that means that if we restrict our scope to some particular machine learning models, then this utility function will be actually 0, and we have some hope to reduce exponential complexity to some reasonable and practical time. So here is the most surprising result that we get from this work. Essentially, if we consider the utility function associated with k-nearest classifiers, we have a later work also studies the k-nearest neighbor regressor. So if we consider it to be the k-nearest neighbor prediction confidence, and then all we need to do is simply just sort the training database according to its similarity to a test point, and then use this recursion here. So all the computation of Shapley value can be accomplished in n log n time, which is extremely fast. So we use this technique and go to some very large database and see what is the value of different training points. So on the left-hand side, you can see this is a test image, and the right-hand side is the top value training points for a particular test image. And you can see if the test image is this is nature, and all the top value training points will also belong to nature class. So this is in that Shapley value. If you use Shapley value to measure the importance of different training points, those high value points will thematically correlated with the test point. Okay. So this is for Kn, but if we consider some general rotative functions, it will be still hard to compute the Shapley value. So the state-of-the-art approach is to actually using this sampling-based approximation. So to illustrate the idea, we need to go back to the definition of Shapley value. Here we consider a alternative definition of Shapley value. It can be shown to be equivalent to the previous one that we discussed. So essentially, the Shapley value of player I is equal to it basically looks at all the permutations and calculate what is the contribution of player I to its to the players precede it in the permutation and average over all permutations. And if you consider the permutation to be a random variable, you can see that the Shapley value is essentially the expectation of the marginal utility averaged across all the random permutations. So this inspires us the algorithm to approximate the Shapley value, which is to use the sample average to approximate this expectation. So the detailed algorithm is like this. We have some random permutations of training points drawn here, and for each random permutation, we basically compute the marginal utility of each training point, and then we average the marginal contribution across different permutations. To talk more about the complexity of this algorithm, we need to formalize what is our notion for approximation error. So here we consider an estimate of Shapley value S hat to be the epsilon delta approximation to the true Shapley value S if the L infinity norm between the between the estimate and the true Shapley value is bounded by epsilon with probability at least 1 minus epsilon. It's really close to the definition of epsilon delta differential privacy. And if we use this, yeah, do you have questions? Okay, sure. So if we use this approximation error notion, then you can actually use some simple bound to derive that this algorithm requires n log n model retraining to achieve epsilon delta approximation error. So this is the state-of-the-art result for approximating the Shapley value. Then the question is that can we do better? Yes?
I can jump with my question. So how do you imagine actually using these to the motivation, I guess, was paying people for their data. But I guess at training, and you're using the test points to determine how much to each of the training points is worth. But I guess we often you do the training, and then we don't know in the future what things this model will be applied on. So how do you imagine? Kind of at what stage and using what test points do we decide how to take?
Yeah, that is a great question. So in machine learning pipeline, you always have this, you collect some data. You oftentimes divide the data into training and testing. You want to, sufficiently test the performance of the machine learning model before deploying it into practice. So we can just use those test data to test the performance of the machine learning model. Yeah.
Let me rephrase Sally's question just a little bit. If you get data over time, right? New people buying a sensor, deciding to participate or not, you can't do the permutation just because you don't have everybody yet. In the same way that you can't test over the whole distribution of possible participants, right?
Yes.
Only sort of incrementally at the beginning. So it doesn't matter who comes first for the outcome that you will eventually pay. Is that direction?
It's really similar.
Yeah, I think this is an interesting extension that we need to consider in the future. So right now we only consider this, offline machine learning, and online is, very interesting direction that needs
to be researched.
Yeah, yeah.
And do the people who contribute the test data need to be paid also?
Yeah, so right now we only consider this training data. It probably needs some more thought about how can we do test data as well. Yeah, those are very good questions. Right. So let me go back to my slides. So we have talked about this state-of-the-art approximation algorithm. So the question is that can we do better than that? So if we, think about what is a state-of-the-art approximation algorithm is. So it basically draws some random permutations and then computes the marginal utility of each player independently. So then the question is that can we do some, use these samples jointly and consider the information sharing between different random samples. So here, let's say we have two random subsets drawn from the training data set. So if the image is shaded, it just means that these two samples are not selected by this random subset. So let's say we have two random subsets. You can see these two subsets happen to have one image in common. So if we evaluate the utility of these two random subsets, and it happens to that all of these two random subsets achieve high utility. So this is a very good indicator that this image that they have in common has very high Shapley value, right? So this means that we can actually, there are some information sharing between different samples, and can we really make use of it to develop more sample efficient algorithm? So the answer is yes. So here is the algorithm. We can actually encode the occurrence of a different training sample using this binary variable. And we consider this utility difference. And our idea is really to design the sample distribution so that this utility difference actually in expectation equal to the Shapley value difference. And if we can estimate the Shapley value difference very well, then we can use a small amount of samples to estimate the Shapley value of a particular training point. And then we'll be able to recover the Shapley value of the rest of the point. So let me tell you the main result. So basically, this new sampling-based approach that employs this idea of information sharing can return epsilon delta approximation to the true Shapley value with only sublinear number of model retraining. Recall that the state-of-the-art requires the superlinear n log n model retraining. And this is really a large improvement when we have a large number of training points. So there are, yes?
Question, when you train the model, if you're trying to evaluate the contribution of one training point, presumably you need to get a really accurate evaluation of the model accuracy. Mm-hmm. Is there some way to, to not do that, to train the model only roughly or something, just to get some kind of estimator of the contribution also?
So in this, so I think it depends on how you formulate the utility function. So if your utility is really like the accuracy of a model, if you train it to best, then we will need to train every model to the best in order to calculate the Shapley value. But if your formulation of utility allows some, error during training or allow some errors in terms of prediction, then we can probably train each model subject to some error and then compute the Shapley value.
So I guess I'm just if the contributions are, I don't know what n is in your applications, but mm-hmm. if the contribution is on the order of 1/n, mm-hmm. even once you've trained the model, just evaluating the classification error to that level of precision requires a huge number of model evaluations.
Yeah, that's exactly the problem. So, so as I said, so if we have a KN nearest neighbor algorithm, it will be very fast because we don't need to train the model. So if we consider deep neural network, as you said, it will be very hard to even evaluate the testing accuracy. So what we do in the experiment is that we have a deep neural network. What we can do is that we use the deep features and replace the last layer with a KNN, so that we can make use of the fast algorithm associated with KNN to compute the value of different training points. Yeah.
So you only train the representation once.
Mm-hmm. Right.
Thanks.
Exactly. Yeah. So here are some other ideas to make the Shapley value evaluation more efficient. So here is one. So we plot, this is based on an empirical observation from our experiment. So we plot the Shapley value of different training points in a database of size 1,000. And you can see that almost all of the training data have similar Shapley value except a few of them. So this is really insane that actually the Shapley value has this sparse structure if we consider a large database. So then the idea is that how about using compressive sensing, which is a very renowned idea to recover the signal from noisy environments if you have only very few, if the signal has a sparse structure. So here we combine compressive sensing with sampling and get this result that we only require log n number of model retraining in order to compute the Shapley value if the underlying value is sparse. So let me introduce some more ideas. So if we consider a learning algorithm that is stable, so it is stable, meaning that the learning algorithm isn't very sensitive to the removal or addition of a particular training point. And why stable learning algorithm is interesting is because it has some probable generalization error bounds, and also it incorporates a large class of commonly used machine learning models like linear regression and all learning algorithm with proper regularization. So our main result is saying that if the learning algorithm is itself is stable, then we can just uniformly assign the value, and it already gives us a epsilon 0 approximation. So some more ideas to accelerate the computation of Shapley value. Because the Shapley value requires evaluation of this marginal utility difference, and if we just do it naively, then we need to retrain the model in order to evaluate its utility difference. So here is a heuristic to actually approximate the utility difference based on this idea of influence function, and it was developed by it was proposed last century by Huber, and then redeveloped by this paper in 2018, and they try to compute try to use the influence function to approximate the effect of removing one training example and see how the performance changes. So we use the influence function as a heuristic to compute this utility difference, and it will give us a speed up in terms of to compute the Shapley value. And another idea is that Shapley value looks at every subset in the collation. So how about we just look at the largest subset without looking at every one of them? So apparently this can also accelerate the process of computing the Shapley value, but it no longer satisfies the properties that we discussed before simultaneously. So there is a trade-off between the rigor of the data valuation mechanism and the computation efforts that you use. So yeah, here are some results. We compare, we first look at what is the approximation error of different ideas that we developed. The x-axis is the true Shapley value, which is produced by the state-of-the-art approximation algorithm, and the y-axis is our estimate based on different ideas. And you can see that our new sampling algorithm, and if we use the influence function heuristic, it can all estimate the true Shapley value very well. And if we use KNN, because the utility function changes, then it will have some discrepancy from the true Shapley value based on logistic regression. And if we use largest set influence, then of course there will be even larger discrepancy. And on the right-hand side, it is a runtime plot. And on the very top, we can see that the state-of-the-art sampling algorithm performs very bad when we have training. We have a lot of training examples, and our new sampling performs slightly better. And if we use more heuristics, then we can get more acceleration. And the K Shapley value is, of course, the farthest one up to now. So here is a plot just to show you that the Shapley value actually coincides with our notion of value. So we actually do experiments which try to divide the training set into two parts. One part we just keep as it is, and the other part we add some artificial noise into the data. And you can see as more noise added into the data, the Shapley value of those noisy points will be lower. So essentially, this is just saying that just confirms with our intuition that Shapley value is a fairly good notion for data value. So just a summary, so we have introduced a framework and some formalization of data value, and we have discussed a repertoire of efficient algorithms to compute the Shapley value. And we are actually currently building a system, a data marketplace together with Stanford Hospital. So the idea is that we want to pay the patients for their data. So there will be some buyer whose payment will be distributed to different patients. And our Shapley value data valuation mechanism is actually implemented on this data marketplace. And right now we are doing this clinical trial. And for future work, so we really need to consider how can we encode the personalized privacy preferences into this data valuation framework, because right now the data valuation is solely based on the payments to each user is solely based on how much their data, how useful their data is for some specific machine learning task. But some people might feel more conservative about privacy than the others, so how can we deal with that? And also we really need to develop more efficient algorithm for broader class of machine learning models like gradient boosting and so on and so forth. So as you can see, there are more questions than answers. So this talk is mainly meant to invite discussions and more efforts towards this direction. So how much time do I?
Few minutes plus question, maybe 5 minutes.
Okay, I will just quickly go through the rest of the talk. So in the second part, I will and basically introduce some approaches to models of privacy and utility, and I will illustrate it through an example in smart buildings. So let me directly go to the problem that we are trying to solve in smart buildings. So in smart building, we have some sensors that collect the occupancy measurement, and those measurements will be used to adaptively control the heating. HVAC just means heating, ventilation, air conditioning system in the building. But there is a recently published attack saying that we can actually recover the occupancy, recover the location trace of different people from those occupancy measurements. The idea is that if the attacker knows the owner of different office, then he can associate the change of occupancy to the location trace of different people. So that is the problem that we are trying to solve. So what we do is that we propose this new notion of inferential privacy. So the idea is that we consider attacker, and there are some private data and public data that the attacker can see. So before seeing the public data, he has some cost associated with the inference about the private data. And after seeing the private data, his inference is updated. And this difference between two inference costs really characterize how much privacy is leaked through the publication of the public data. So if the cost is logarithm loss, then this privacy leakage becomes mutual information. So, so in the rest talk, we'll be using this mutual information to characterize privacy loss. And the inferential privacy is different from differential privacy in the sense that if we have a very good adversarial model, then I will give you a very explicit characterization of the privacy loss. So in our problem, then the private data will be the location, and the public data will be the occupancy. And we are trying to solve a problem that try to minimize the privacy loss subject to some control performance constraint. And we will evaluate this control performance through simulations. And it turns out to be a linear programming and can be quite efficiently solved. So let me just give you the result. So this is just to show the privacy utility trade-off for different mechanisms. So if we compare with fixed schedule where you don't need to collect any data, but of course you have high control cost. On the other side, you can collect highly accurate data, but of course the privacy loss is very high. So what this plot shows is that we want to have this trade-off between privacy and utility, and you really have two options. One is to replace your sensor by a cheaper sensor that is equivalent to adding some multinomial noise to the occupancy measurement. And this plot is really showing that you can do better by solving this optimization problem and achieve a better privacy utility trade-off. So some other works in the space that we have been doing is that I have talked about how to distort this sensor data in order to guarantee more privacy. But since the cyber physical system is a closed loop system, can we even adjust the control and incorporate privacy laws as part of the control objective? So we have this very interesting work try to study how can we jointly design control and sensing for privacy in cyber physical system, and we have some interesting results saying that if we have linear Gaussian system, then the problem of control design, the problem of privacy mechanism design can be completely decoupled, and that will be efficient if we want to design those mechanisms. And we also have some work try to identify the redundant data for a particular application. So in the interest of time, I want to briefly go through some works that is happening in Don's group. So most of them are considering how to really deploy differential privacy in practical scenarios. This one is about how can we design differentially private convex optimization problem, and this is a paper to be appearing in this year's Auckland conference. And the contribution is that we have this convex optimization that leverage off-the-shelf optimizers and doesn't require any hyperparameter tuning in order to achieve differential privacy. And there is also a large-scale empirical study that compare different convex optimization problems that have differential privacy guarantees. So another project called Duet. This project is really try to automatically prove differential privacy in practical systems. It achieves this goal by actually design a domain-specific programming language. And the last project I want to mention in Don's group is Chorus, which is similar to what Michael talked about. So this kind of designs a bridge that facilitates adding privacy into some query engine, and it can be usable by some non-experts. So to summarize, I have introduced two perspectives. We start from how to value data and how to make it is reasonable, it is fair, and most importantly, make it computational tractable. And I also go through some method to model privacy laws and utility, and also some works in Don's group. And with that, I would thank you for your attention, and I'm happy to take any questions.
Questions?
Can you say a little bit more about how you model the adversary in terms of what they learn, so how they sort of compute that difference in bits of machine learning in the context of these smart buildings?
Sure. So in this case, we have a very explicit adversarial model, which is taken from another paper. So they study how to attack how to recover the location trace from the, let me go back to this, how to recover the location trace from the occupancy measurement. So what they do is that they use a factorial Markov, hidden Markov chain, and the hidden state will be the location trace, and the observation is occupancy measurement. So they basically do this inference on the graphical model to recover the location trace, the hidden state. So we have a very clear model of attacker in this case. Yeah.
Okay. There is no other question. Let's thank the speaker again.